Okay, so let's wait for 5 more minutes because recently the timings have been changed. So let's wait for 5 minutes and after that we will start.
Yeah, sure.
Is there any other class also regarding this live session?
Yes, by Mr. Maiti. So he
Okay,
conducts on every Tuesday.
every Tuesday.
Yeah,
Okay, timing
6 to 8.
6 to 8.
Good evening, Amit.
Good evening.
How come this we shifted from Friday to Sunday? Was it on
Uh,
demand or
Actually, it's due to my office work. So from eh, last week onwards, I'm having some other work on Fridays. So that's why I was not.
no, okay? If it is
Yeah,
Sundays, it is good for us also.
yeah,
That's my view. My preference because on weekdays, finishing our office work and then getting into it
yeah.
is a tough, very
It's
tough
very
task.
hectic. Yeah,
Yeah.
really.
So Sunday is preferred. I don't
And
know
time
about
is
others.
also good. I think 4 to 6. So it's free time.
Yeah, Sunday 4 to 6 is also good. Because
So
I
when
don't
did
want
you
to miss you.
receive this information? When did you receive
It's
this information?
yesterday or today. Today morning I got a SMS also.
Okay, okay. So did you try to join on Friday also?
Yeah, I was looking at it. I was looking at it. Then I realized, okay, since it is not there, I was good. I knew something will happen over the weekend. I was
Okay.
confident about it. I was very confident about it.
Okay, nice. Okay, so I think we have waited enough. So now I'm sure that everyone have received the information about this reschedule of this class. So they will join, or let's say maybe from next class onwards they will join. So okay,
Amit, one question.
yeah.
The sessions, what happens on Tuesdays, is it the same or is it totally different? Because I have not been able to attend any Tuesdays. I
So
couldn't
actually
attend.
the session, the agenda is same. The tutor
Okay,
is different.
okay, okay.
So maybe the tutor is different. So maybe the questions, the
Uh,
content, that will be different. So if you want more content, so you can attend both classes, and if you think that this
Okay.
content is enough, then it's fine. But
Mhm.
the pattern will be same every week,
Oh,
and he or she will also discuss the previous week session only.
okay. Right. Okay.
Yeah.
Okay.
Okay. Okay. So
Okay.
good evening, everyone. I welcome you all to the live session number 6 for the course Hydrogen Energy Production, Storage, Transportation and Safety. The course instructor is Professor Pratibha Sharma from IIT Bombay, and I am this course TA Amit Kumar Sharma. So every week now onwards, we will have a live session on each Sunday from 4 p.m. to 6 p.m. Those who are not able to attend live session, so the video recording of this session and the PPT that I'm using here will be provided to you from the NPTEL team. So you can attend it later. So the purpose of this session is to discuss the previous week's assignment questions and also go through the concept of the previous week. So you can have a short revision and you can also have practice on assignment questions. Okay, so let's start with today's class. So this is the course outline. So we have already covered the production part. We have covered production part. Now we are in on the storage part. Okay, so today we will see the storage part. So the question number 1 is, what is the density of liquid hydrogen at 1 bar? A 80.1 kg per meter cube, 65.3 kg per meter cube, 70.9 and 0.089.
0.089.
Okay,
D.
we have one answer, 0.089. Anybody else? So it's
The
a
70.9.
yeah, nice. So we have another answer. So now we have two answers. So you should both think about the question because we have two answers. So but only one answer is correct.
Yeah, it is C.
Okay. So I think you have identified your mistake.
Correct. Yes.
Yeah.
Liquid.
So
It was
liquid.
liquid. Yeah.
Yeah. So always read question carefully. So what is the density of liquid hydrogen? It is mentioned liquid hydrogen at 1 bar. So what about option D? So what is the density? Why? So for which hydrogen this density is?
Gas.
Yeah. So this one will be for the gas at at 1 bar, or you can say the NTP. But it is mentioned about the liquid hydrogen. So we know that this option will not correct. Now A, B, C. So they are very near. Then you need to recall your class notes or you need to calculate if you have some kind of factor in your mind or that. So the correct answer will be C. Okay, so now let's see something more about the hydrogen density. So we know the LHV, lower heating value, and higher heating value. Okay, so if you compare the LHV and HHV of hydrogen with other fuels that we commonly use, methane, LPG, gasoline, so you can see the difference. So the LHV is more than double from methane, LPG and gasoline. So the for hydrogen is having the highest LHV, 120 megajoule per kg, HHV 142 megajoule per kg. Anyone want to tell me the difference between the LHV and HHV? What is the difference between lower heating value and higher heating value? Anybody?
I think if hydrogen is directly bond, then it is LHV. I don't remember exactly, but I think that.
no. So actually LHV and HHV. So there is a method to calculate the calorific value of a gas, or like any gas, or you can say fossil fuel, any combustible substance, or like any material that can have some energy inside that and having some calorific value. So we can measure the calorific value, and so the name is, I think it's bomb calorific meter, I think. Let me cross check. Yeah. So there is a bomb calorimeter which can be used to determine the calorific value of solid and liquid fuels. Okay. So in which we can measure the heating value. So yeah, we will do the burning part, but not directly. Okay. So in that method, we will have some kind of system. So which can show us the, okay, this fuel, liquid or solid fuel, have this much of energy. So now there are two types of energy, LHV and HHV. What is the difference? So you can see number. So it's 120 megajoule, 142 megajoule. So there you can see the difference is 22 megajoule. So for methane also, it's 50, 55.6, LPG 46, 47, gasoline 44 is 47. So when you calculate the higher heating value, then you consider that, like when you are measuring the calorific value in the instrument, then you are considering the output, because it will generate when you will burn it. So there will be some H2O, water vapor. So you are considering this water vapor has been condensed and is in liquid form. Okay. So it means that you are having the heat of vaporization. Okay. From vapor to liquid. So that heat is also calculated in the calorific value. So that HHV is higher than the LHV. In LHV, you are considering that your water is in vapor form. So this is the major difference. Okay. So in LHV, the water is considered in vapor form, and in HHV, it is considered in the liquid form. So the difference is due to the latent heat of vaporization for water. Okay. So for more detail, you can also read about bomb calorimeter. So normally in our practical application, we consider the LHV for efficiency calculation. Okay. Because that's a realistic approach to consider the LHV. If you consider HHV, high heating value, for efficiency calculation, then your calculation will be not correct, because in actual, when you will do some, when you will use the fuel in practical application, okay, your water will be in the gas form, in the steam form only, not in the liquid form. Okay. So it is depend on the mass basis. Now let's see on the volume basis. So hydrogen at normal temperature and pressure, the density is 0.089 kg per meter cube. So in this question also it is mentioned liquid, then it is 70.9, but otherwise it is 0.089. Now if you increase the pressure, so at 200 bar, 350 bar, 700 bar, so your density is increasing. Okay. Similarly, you can see the density for gasoline and diesel. So at liquid hydrogen, at 1 bar, the density is 70.9 kg per meter cube. Okay. And for solid state, it is 100 kg per meter cube. If you see the density of gasoline is 32 megajoule per liter and 36 megajoule per liter. Okay. So what do you think from this mass basis and volume basis? What is the your understanding after getting the knowledge of the density in on mass basis and on volume basis? What do you think about hydrogen now? Anybody? The data is in front of you, so you know the density on the mass basis. Sorry, on the value on the calorific value on the mass basis and density on the volume basis. So what do you think? What is the understanding based on this data?
Uh, Handling hydrogen or at NTP or any other pressure is not as efficient as any other comparative liquid fuel.
Okay, anybody else? Okay, so on the
Energy,
from
yeah, when the pressure increases from 200 to 700 bars for hydrogen, and then the energy also increases on volume basis per liter basis. So at 200 it is 200 bar it is 1.8 megajoule. At 700 bar it is 4.82 megajoule per liter, and density also increases.
okay, yeah. So this is the one point. Another point is that if we compare, because we know the LHV is okay, it's fine that hydrogen is having more than twice the LHV of fossil fuel like LPG, gasoline. But see the difference in density, it's huge. Okay, suppose if you need like 1 kg of a fuel, like if you have 1 kg of gasoline, then it will give you 44 megajoule of energy. Okay, then for this much energy you will need around 300 to 400 gram of hydrogen only. Okay, zero point 0.3 to 0.4 kg of hydrogen. But see the density, volumetric density. So to have that much of gasoline, so for gasoline you can see that you can store 32 megajoule per liter, but for hydrogen 0.01 megajoule per liter only. So this is the difference. Okay, so you need to have so much of volume to store the hydrogen. That is the main issue with the hydrogen. Okay, the storage. So because the volumetric density is very low, so if you are storing the hydrogen in gas form, then you need to have so much of volume because the volumetric density is very low. But we need this much of energy. So to have this much of energy, you need a huge storage if you are using hydrogen as a fuel. But if you are using the gasoline as a fuel, you need to have a very small storage. So that is the one point. So that the thing is that if we want to reduce the volume, then what we can do, we can increase the pressure. So if we increase the pressure, so the density will increase. So now you can see we can store more hydrogen per meter cube. If you go in the liquid form, then you can see we can store up to 70.9 kg per meter cube. But still, if you want to convert the hydrogen into liquid form, then you need to also provide some energy. Okay, so these are the thing. So when we are considering the hydrogen, so we need to, so based on this data, when we are when we want to work with hydrogen, then we need to also see the cost, durability, its charge discharge rate, refilling time, duration of storage without loss, okay, faster response, fuel quality, efficiency, safety, weight and volume. So these are the things we need to consider. So now it's a comparison. So suppose you need 5 kg H2. So basically you need the heat that can have 5 kg of hydrogen. That much of heat you need. So see the volume difference. So if you use the gasoline, then only you need to store this much of energy. You need only 49 liters of volume. But if you are having hydrogen at NTP, and to have this much of energy that 5 kg hydrogen have, so you need to have 11,940. Okay, 940 liter of volume. If you have hydrogen 300 bar, then it's reduced. So 212.5 liter, then 125, then 111, and liquid hydrogen it's 75, and solid it's 33.3 only. So see, the volume is reducing. Okay. So as you are increasing the pressure, the volume is reducing, you are improving the density. But still, compare with the gasoline, so it's much lower. Okay. So now the question number 2. The operating pressure range for storing hydrogen in salt cavern are selected with reference to which of the following pressure? Lithostatic, atmospheric, hydrostatic, vacuum.
Sir, lithostatic pressure.
Okay, we have one answer. Anybody else? Okay. So the correct answer is A, lithostatic pressure. So as we are storing in the salt cavern, so the lithostatic pressure, what is the meaning of lithostatic pressure? So what is the meaning of atmospheric pressure?
Atmospheric pressure is a 1 bar, roughly 1.01325 bar, while lithostatic pressure is a pressure exerted by the salt material or sediments, which that solid material that applies pressure to the stored gas.
Yes, yes. So because we are having, like suppose this is the earth crust and we are having some here. So you can see the all this rocks that are surrounding it. They will create some pressure over here. Like you can say the hydrostatic pressure in the fluids. Similar kind of pressure. So that is the lithostatic pressure. Atmospheric pressure we all know. Vacuum pressure we know. So the correct answer is A. So now let's go through some history of underground storage. So in 1950, Ontario gas field uses used for natural gas. Underground hydrogen storage similarities with underground natural gas storage. So because UHS is similar to the natural gas storage. So in 1950, this gas field used for natural gas. The 1960 Volters. So they are having some problem with the UHS. So similar like 1979 and so on. So recently in 2020, so she et al. Investigated the potential of a storage of hydrogen and natural gas blend into a depleted gas oil reservoir, which has already been used for natural gas storage through a series of experiments. So recently they did some experiment to use a depleted oil and gas reservoir, which was earlier used for natural gas to store the hydrogen. And also in 2020, Nayan Murthy et al. Proposed a normal Wiggy dual hesitant fuzzy set For UHS site selection based on the 5 criteria, including the technique of operation, investment cost, social, economic, and risk factors. So you can search these papers from these authors to read more about recent development in the underground hydrogen storage. Okay. So what are the advantage and disadvantage of underground hydrogen storage? So advantage, so we can have long-term, large-scale storage because on underground we can have so much of space available in underground, like the oil wells, salt cavern, and all. So we can store so much of hydrogen. It's economical because the space is already created there. Okay, so you just need to do some extra thing, and it's economical in the way that if you want to create that much of space on the earth, then to maintain the pressure, to develop that and all things, so it will need huge investment. But for underground hydrogen storage, it's economical. It's proven technology. So we have seen, like from 1915, we have stored natural gas and all. So it's proven technology. It can give good performance, less microbial contamination, and it's safe. Also, it having some disadvantages, integration challenges, high purity hydrogen. Because if you are suppose you are storing hydrogen in a oil depleted well, then maybe the surface of that well can contaminate the hydrogen. There can be some reactions. Availability of such geological structure. So we all know that it is not available everywhere. So it is a big issue regarding the availability of these geological structures. Okay. So also safety. You need to monitor it properly, and proper regulatory framework, because if you are storing a huge amount of hydrogen, then there will be some regulatory framework also. So you need to compile all those frameworks. When we store hydrogen, then we also having accretion gas in underground hydrogen storage. So what is the meaning of this? If you have gone through the classes, let me know.
Sir, cushion gas basically it will pump out the hydrogen that is stored in the underground. Basically, one gas is used for to pump out that another hydrogen.
No, no, it's not fully correct. It will help to pump the hydrogen, but suppose this is your
As I remember, it is the other gas other than hydrogen. It increase the density and which also helps to pump flowability and density. So maybe ammonia or nitrogen inert gas. So by that we can easily pump out the hydrogen and also store more hydrogen. So that is.
okay. So just a minute. Am I visible? Because I think I'm having some connection issue. So are you able to see my PPT?
Yes, yes, we can see.
Okay, okay. So I think I was having some network issue. Okay, so you were saying something? Please repeat.
Yeah, I was saying it is a other gas other than hydrogen. It increases maybe density and also increases the flowability.
Yeah, right, right. So basically, suppose this is your underground cavity where you want to have hydrogen storage. Okay, earlier it was used for, like, it was a part of like coal mine or like oil well and all. Okay, or salt cavern. So if you directly pump the hydrogen inside, okay, then the hydrogen will fill in this cavity. Okay, then maybe it will react because these walls are having some kind of chemical, so they can react. There can be some biochemical reaction, maybe some microbes are also, or because it's very like old geological structure, so maybe there are some microbes, some kind of chemical, so there can be some reactions. So then those reactions can introduce impurities in the hydrogen. So when you pump out, then those impurities can also come. And also you need to, because suppose if you want to have, we know the challenge of, we know the challenges with hydrogen storage. Okay, so we need to compress it to a very high pressure. Okay, so suppose it's totally empty and it's a very large space. Okay, so to have 700 bar pressure to in that large space, you need to pump so much of hydrogen. But suppose you don't have that much of hydrogen, then this space will not able to maintain this pressure. Okay, maybe it can only, because suppose you are having x kg of x tons of hydrogen, so you pump x ton of hydrogen in this cavity, so it can go up to 200 bar only. But you need to have it 700 bar. That's economical to you. Otherwise, you need to again compress it. Okay. So then what we can do? So to avoid these disadvantages like the contamination, to maintain the pressure, we can first add a different gas in this cavity. We can add nitrogen. Okay. So first fill this cavity with that gas. So that gas will occupy some space. Okay. So that will occupy some volume. Now you can introduce hydrogen. Hydrogen is lighter gas. So the other gas will be near this boundary only, because that will be heavy as compared to the hydrogen. So hydrogen will be in middle. And now you can compress it because the same, because already so much of space has been already occupied with nitrogen or any other cushion gas. So you need to have, now you have small space and more volume of hydrogen to pump. So now you can go up to 700 bar or larger. So this is the benefit of cushion gas, and also it helps in the pumping. So it's as you have larger pressure, so it will help, and it also have some other benefits. So you can attend the class, the MEMS class, and also go through the reference book. But these are the some main benefit of the cushion gas. Okay. So when we are having the underground hydrogen storage, so there are some parameters for site selection. Like we need to see the capacity, security, physiochemical, geo and biochemical challenges, and economics. We need to see these. What are challenges? So location suitability, capacity, reaction and contamination, as we discussed, hydrodynamics, leakage. Hydrogen is very lighter, so there can be some leakage also. Water production, environmental issues, and efficiency of process. So these are the challenges for underground hydrogen storage. So the further research and upscale pilot projects are needed. So as we have seen in the history that recently in 2020, two or three authors have done some experiment on hydrogen storage, and prior to that some other have already done some experiments. So still, but there is some more research is needed in this area. Hydrogen storage site selection methods need to be expanded to less well understood regions. Improved monitoring procedures are required to assure that hydrogen can be stored safely. So the monitoring procedure, we need to improve those. Realistic simulation models to predict performance of hydrogen storage, and further refine to model the process completely. So these are the areas where we need to work. Okay. Now, what are the major properties of hydrogen? We have already covered less density, less viscosity, high mobility, better efficiency towards withdrawal. Okay. Less viscosity, solubility, solubility is less, so lower loss further reduced in presence of salts and hydrogen leakage. So we have, you can see the options for hydrogen storage, salt caverns, depleted oil and gas reservoirs, and aquifers. So these are the locations where we can store the hydrogen. Okay, so these are not only, these locations can not only be used for hydrogen storage, but still, but they can also store CO2. They can use as town gas storage and methane storage. Okay, we can also use abandoned coal mines, lined hard rock caverns, and refrigerated mine caverns. We can also use these. So the selection of the location will be depend on the media, the cavern based storage, and trapping capacity and properties of gases. Okay. So the property of gas is important because, as you discussed, you are having a layer. You need to study that. Suppose if you are storing a gas that is having direct reaction with the inner surface of your cavity, then that can contaminate the gas. So you need to look into that. So the properties of gas you need to understand. Now let's go through the salt cavern. So it's mostly cylindrical, artificial pits in thick underground salt deposits built from the surface by injecting water in a controlled manner into a well in the salt rock. It's called solution mining. It's based on the requirement and the technical possibility can build up to 2000 meter deep and 10 lakhs meter cube volume, 300 to 500 meter height and 50 to 100 meter diameter, enabling to store large quantity of gas. Pressure during operation lies in the range of 30 to 80% of the lithostatic pressure. The specific geological conditions such as tightness, the favorable mechanical properties of salt, and its resistivity to chemical reactions. So we need to see this. Suppose you are having your salt is reacting with the gas, then it's not good. So you need to see that also. Viscoplastic attributes of evaporitic rocks help with their better sealing function. Because hydrogen is a very lighter gas. So if there is small cracks in the rock, so maybe, and that crack is connected to some other cavity, so there can be some leakage. So you need to also consider that. Additionally, the high saline condition restrict the consumption of hydrogen by microbes. Depth of the caverns affect the capacity of storage. Higher depth leads to more pressure and in turn more compressed gas. Okay, so because we know if we are storing hydrogen, we need to have more pressure. So higher depth can have more pressure because higher depth will have a higher lithostatic pressure, and we know that we can go up to 30 to 20% of that pressure. In a lower depth, lower amounts of cushion gas needed reduce the cost of operation. So important issue is to supply large amount of water for leaching of cavern and securing the proper disposal of the brine obtained in the process. Technical and economic factor, the distance from the pipelines and the availability of water, cost to build salt chambers less than other underground projects, as well as all process are done from the surface through a single well with enough casing and installation to transmit gas, that too subject to the size of cavern. So these things are about the salt cavern. Now the aquifers. So these are the porous and permeable media where their pore space are filled by fresh or saline water found all over the world, making them a good option for underground hydrogen storage. Now there are some conditions for deep aquifers. It should have good reservoir characteristic of host rock. Second, the presence of an impermeable layer to prevent migration of the gas being stored. So there should be an impermeable layer. Okay. Otherwise, there will be leakage of the gas. So hydrogen is injected into the aquifer filled with water due to the density difference between gas and liquid. The liquid will displace downward or away to the sides. The pressure of porous media is increased because of adding hydrogen in the same volume without withdrawal of the liquid. So as we discussed earlier that you are having this cavity, and if there is liquid already, so if you push the gas, so your liquid is heavier, so it will move towards the side and you can have less volume, so you can store more hydrogen at higher pressure. When hydrogen is withdrawn due to the movement of gas liquid interface, the liquid can also be produced simultaneously with gas, which is an advantage of hydrogen in aquifers. So when you're pumping out, some part of liquid can also go with the hydrogen. So there can be biochemical reaction, leakage, or reaction of hydrogen with the minerals in the reservoir rock. The further structure and rock properties of the aquifers that are needed to characterize such subsurface formation rarely available. So as of now, pure hydrogen storage is aquifers is not reported. The storage projects of town gas with a composition of around 50% hydrogen, 50% methane reported in Europe. Okay, in Germany, in Czech Republic, and in France. Now the depleted oil and gas reservoirs. So hydrocarbon bearing geological trap is kept with an impermeable layer, cap rock, and is supported with an aquifer from the bottom or edges. So it's most appropriate option for underground gas storage due to their well identified geological structure, good tightness and integrity of their cap rock, and pre-existence the necessary surface and subsurface insulation. So due to these things, they are suitable. Depleted gas reservoirs are well characterized, information known. The tightness of the cap rocks of depleted gas reservoirs has also been proved. The existence of the remaining gas in a depleted gas reservoir is considered as an advantage because it can play the role of cushion gas. So because if you are having a gas reservoir, then there will be some gas available, so that can already used as a cushion gas. So it can reduce the cost. But also disadvantage if remaining gas is able to reduce the purity of hydrogen. But if the amount is so much and also there can be some reactions, then it's not good for the purity of hydrogen. When planning and designing facilities for UHS in a depleted gas deposit, it is important to cease gas extraction at an optimum time, allowing storage to be created in a shorter time and at a lower cost. So these are the things you need to consider. Okay. So newly created UGS facility usually attain their planned exploitation parameter in about 5 years. Suppose if you want to create a new facility, so follow these steps and you need to have at least 5 years. Formation water that invaded the gas deposit after the cessation of its exploitation are being expelled during this time. So the conversion of a depleted oil reservoir to a user site requires comprehensive study. Any is residual oil in the reservoir or not? The possibility of chemical reaction, conversion of hydrogen into like methane will be increased, decrease hydrogen purity. Okay. So these are the things you need to consider when you want to have a depleted oil reservoir for a underground hydrogen storage. So now these are the worldwide operating underground hydrogen storage projects. So you can see this one is in bedded salt dome, then cavern, aquifer, and depleted gas reservoir in Argentina. Okay, and depleted gas reservoir. So the percentage of hydrogen 95 to 10. It's operating. So you can see and you can also go through this paper to learn more about these. So from these last 3-4 slides, we know that the underground hydrogen storage can be, we can store pure hydrogen or we can store mixture of gases like 50% hydrogen, 50% methane and all. So from the CO2 experience, we know that it has a long, we can store for long term, but there is a risk of corrosion and leakage also. So from the experience from natural gas storage, withdrawal frequently, loss and leakage more, and helium storage. So for the aquifers, injection pressure higher than aquifer natural pressure, less density, viscosity. Withdrawal at fixed rate difficult. So we cannot withdraw at a fixed rate. Loss inflow will be there, reservoir and reservoir pressure reduction will be there, expansion of gases can be there. Okay. The porosity, permeability, geometry, saturation and well location, density, viscosity, these are also will change the variation in aquifer flow behavior. So this will also change the withdrawal of hydrogen. Gas cannot be completely recovered if you're not using the cushion gas. So use of cushion gas is good. So you can, as a cushion gas, you can use town gas, CO2, CH4, N2 to improve pressure and efficiency. So these are the options for town gas, for the cushion gas. So dissolution in oil, in depleted oil reservoir. So if you are using the oil reservoir, so some hydrogen will be dissolved in that. Losses, because if your rocks is having some kind of microbes, so there will be some reaction, micro or macroscopic trapping, dissolution in connate water, extent of fingering, dissolution, diffusion, mixing, surface tension, solubility, water saturation, capillary effect, and withdrawal rate. So these are the reason for losses. So geological, biochemical, microbial reaction can be happen in this underground hydrogen storage due to the ions, microbes, minerals, undesirable elements and catalyst. So you need to have regular monitoring for carbon isotropy, electric resistance, tomography, seismic full wave form inversion, electrochemical and chemical techniques. So these techniques you can apply for regular monitoring of underground hydrogen storage. So in summary, we can store medium to long term large scale storage. Salt caverns have been most promising. Restricted geological location, small capacity, porous geological formation, capacity and local positioning, depleted oil and gas fields you can use, aquifer still under research. So we have seen that there can be so much losses. So you need to be, so these have to be minimized. Site selection, understanding, continuous monitoring, simulation to understand modeling of the process required. So these are the challenges in UHS. Now next question. What are depleted oil and gas reservoirs? Option A, carbon dioxide bearing geological trap kept with impermeable rock, hydrocarbon bearing geological trap with kept impermeable rock, brine bearing geological trap with kept impermeable rock, and hydrocarbon bearing geological trap with kept permeable rock.
Yeah, it is B, hydrocarbon bearing geological trap with capped impermeable rock.
Anyone else? So we can solve this question from the question itself. It is given the depleted oil. So oil means it will be hydrocarbon. So it will be either option B or C. Now we know that when we are storing in underground hydrogen storage, then the kept rock should be impermeable. Otherwise, there will be leakage. So compare the option B and D. So in D, it is given that the trap will be kept with permeable rock. So it can permeate the hydrogen. So there will be leakage. So it's not good. So it should be kept with impermeable rock. The answer is B. For an for an isenthalpic expansion of real gas with attractive molecular attraction, the Joule-Thomson coefficient is positive, negative, zero, not defined. So what is the Joule-Thomson coefficient? So it is mu Jt del T upon del P at constant enthalpy. So it is the rate of change of temperature with pressure at constant enthalpy. Okay. For ideal gas, it is zero. But for real gas, it can be positive or negative. So if it is positive, then gas will cool down. And if it is negative, the gas will heat up. So del T is zero. Del T is less than zero for if mu is positive, and if negative, then del T will be greater than zero for the isenthalpic expansion. Okay. So for the attractive molecular attraction to the Joule-Thomson coefficient is positive. So the correct answer will be option A, positive. So in Joule-Thomson effect, there is a term inversion temperature T, which is a function of enthalpy and pressure. Okay. For the hydrogen, inversion temperature is 202 Kelvin. And at room temperature for hydrogen, the Joule-Thomson effect is the coefficient is negative. Okay. So this temperature is important. What is the value of inversion temperature for hydrogen? It's 202 Kelvin. And what is the value of Joule-Thomson coefficient for hydrogen at room temperature? It's negative minus 0.3 Kelvin per megapascal. Now equation of states. So we know the ideal gas equation, PV equals to MRT or NRT. We know the Cp specific at constant pressure at volume. K is the ratio of Cp and Cv. Okay. So for real gas, the equation will be PV equals to mzRT. So this Z is the compressibility vector. It's a dimensionless quantity. Okay, and we have several models to predict the real behavior of the gas. So this diagram, there are two diagrams. So this one is representing the diagram 1 and 2. So one is representing the density change with the pressure. So we can see three lines. So this one is for ideal gas, this one is for real and Z factor, and this one is for real with van der Waals equation. So you can see the density if we are increasing the pressure, how the density is changing. For the ideal gas, it seems linear. Okay, linear, but not for the real. Okay. So suppose if you are storing, if you are having a gas at 1 meter cube, 20 degrees centigrade, and you are storing at 250 bar. So if you consider the ideal gas behavior, then the mass of that gas will be 21 kg. But if you apply the Z factor and consider the real gas, then it will be 18 kg. So basically, you are overestimating the mass value by 14%. If you consider the gas as an ideal gas, but in real it is not ideal, so you are overestimating the 14% of value of the mass. Okay. So this is showing the value of Z, the compressibility factor with the pressure. So as we increasing the temperature, the graph is coming down, the slope is decreasing, you can see. So it is minus 50, then 0 degree, 100 degree, and 200 degree centigrade. Now a numerical, what will be the mass of hydrogen stored in kg in a hydrogen compression process at a pressure of 300 bar, temperature 298 Kelvin, volume 1 meter cube, considering an ideal gas and real gas equation. If you're considering real gas, then the Z value have given 1.1879. Try to solve this. Use equation of states for ideal gas and real gas with value of Z. Be careful with the units. So the ideal gas equation is PV equals to MRT. P is the pressure, V is the volume, M is the mass, R is the gas constant, T is the temperature. You have given the data in the question. So the value of M will be PV upon RT. Solve it. Let me give you the value of R equals to 8.314 joule per mole Kelvin. Anybody, are you trying to solve this? Please let me know if you're trying.
Sir, for me, aim is coming 1.121. I don't
Okay.
know. Maybe I'm mistaken with the unit.
Yeah, units. Yeah, units is very important. So let's try for 2 more minutes. Check your units and then we will solve it. Okay. So what is the value of pressure?
300 bar.
Temperature is in Kelvin, 298
298. Okay, sir.
Kelvin, and volume is 1 meter cube.
1 meter.
So I think it's in meter cube, and for this also the value of R is
8.31.
8.314 joule per mole Kelvin. What is the unit of joule? What is the unit of joule? Okay, joule is Newton into meter per mole Kelvin. So okay, so this is in Newton, meter, mole, Kelvin. This is in meter. This is Kelvin. So this we need to change this bar actually. Okay, so it will be 300 multiplied by how much? What is the convert this bar into Newton per meter square? Convert into Pascal. How much?
10 raised to 5.
Yeah, 10 to the power 5 what?
Pascal.
Pascal, and 1 Pascal equals to 1 Newton per meter square. Okay, so it will be, you can say, Pascal. Then 1 Pascal equals to 1 Newton per meter square, so it will be 300 10 to power 5 Newton per meter square. Okay, now the value of M is PV upon RT. Now every unit is in the sink. So now put these values. So 300 into 10 raised to power 5 volume 1 on R 8.314 T298. Now solve it. Let me know the value of M.
It's 12108 grams.
12.108.
108
What will be the unit?
kg.
Kg. Nice. Let me know
So
how it
it's a
will be in
mole.
kg. Yeah. Okay. That's why I told you be careful with the units. So I think here
Yeah.
only you were doing mistake. So see
Yes.
the units we are putting in Newton meter mole Kelvin. So these only. So now let's just only put units. Okay. So for the pressure, it will be Newton per meter square. For the volume, it will be meter cube. For gas constant, it will be Newton meter per mole Kelvin. And for temperature, it's Kelvin. So this Kelvin cancel out, Newton cancel out. This meter square and this meter will become meter cube, and they will cancel out with this meter cube. So what is the remaining unit? Mole. It is in denominator, it will give in the numerator. So the value of M will be in moles. But do we have any option for 12.102 in option in our given options? So there is no matching value in our options, but we are using the correct formula. What is the issue? Anybody?
Sir, actually, it is not point is not coming. It is coming 12108.
Okay, let me check. 12108.
Yeah, 12108.
Okay, then 300.
So yeah, kilopascal, we have to convert in kilopascal. So 10 we have to divide again by 1000. So it would come 12.108. It's correct. 12.108 mole.
12 point.
Is it coming correct or not?
Yes, yes, it is correct.
Yes, correct, sir.
Can you please say how?
Only thing is that Pascal and kilopascal we have to convert.
So yeah, so it's still right actually, no issue. So suppose if you are having this is coming at 12108, right? 0.62 moles. Okay, no issue. So now, is there any option? Is there any option? Now, how we will get the right answer? So as we have also
Well,
checked with the units.
Mole,
We have,
mole, mole to mass conversion.
yes, nice. So we need to convert the mole to mass. Now convert it. What is the molecular weight of hydrogen?
Around 40 grams per mole, right?
this student.
Around 40,
So
40, 40.
40? No,
no,
40.
two.
We just multiply by 2.
Yeah.
Yes.
So it's 2 gram per mole, or you can say 2 kg per kilomole. Okay.
Okay.
So if you are 2 gram per mole, because our answer is in mole, so multiply with 2, then you will have mass in grams. So let me know the answer. Multiply this with the 2.
24217, sir.
24, 1, 2.
217.
Okay, 1 to 7,
217. Huh?
24217.
217. 24
2, 4,
217.
2, 4, 2, 1, 7.
217.
It will be in grams. Now see the
Yeah.
question. We have asked in kg. So now convert this gram into kg.
24.2.
So 24.2 kgs.
24.21 kg. Now check the
Yeah.
options. So 24.21. So actually we have three options: 24.41, 24.5, 24.14. So that's why we need to, like, the value of this value of R, or the exact value of the molecular weight. So if you take those value correctly, then you will have exact right answer. Okay. So we have 22.24.21. So it will be near to this also, this also. So we need to check. Okay. So try to have the exact values, then you will get the right answer. So for this question, because the
If
main purpose is to
we
show
can
you how
check,
to solve this.
yeah, we can
When
check
we
it
check
by
the
Z value. Okay, so
Yeah.
it will be B.
So if you
value
check
of
the
R, we can take,
yeah.
R is
So
8.31446.
yeah. So
So
if
then
you
we'll
take the
get
exact
exact answer.
value 31446, then you will have the right answer. Okay. So if you now just for the value of, if you have given, this is the for ideal guess. Ideal guess. Okay. Now for the real guess, you need to consider the value of G also.
So I think the answer is B, sir.
Yeah. So the answer is B. So the answer will be 24.41 for the ideal guess and 20.55 for the real guess. So what will you do for the real guess? Just divide the value, this
Divide,
value
yeah.
by the Z.
1.1.
Okay. Because we know that for the real guess, PV equals to M Z R T. So for the real guess, there is also a compressibility factor Z here. So when we calculate the value of M, so this Z will come in the denominator. So as we have already calculated the value for ideal gas, so just use that value and divide with the value of Z. You will directly have the mass for real gas. So any doubt in this calculation? So the main thing, so whenever you have questions in your assignment or in your exam, be careful with the units, because the formula is very simple. Anybody can use that formula, but the trick is in the units only. So be careful with the units. Every unit should be similar. Okay, so is it in kg, bar? So you need to have similar units. Then only you can do the multiplication or division. So the correct answer is B. Next question. The compression work is maximum for which of the following process?
Isentropic ideal gas.
Yes. So the correct answer will be D. So the compression work is maximum for isentropic ideal gas compression. Okay. And it is minimum for the isothermal compression. For isentropic, it is maximum. Okay. And if we are having single or multi-stage compression, it can be isothermal. And if there is no cooling in between and there is no molitor P ratio, then it is isentropic. So now let's go through more about hydrogen compression in isentropic process. The formula for the isentropic compression is gamma upon gamma minus 1 RT1. The pressure ratio P2 upon P1 raised to the power gamma minus 1 upon gamma minus 1. So if you try to remember your basic thermodynamics from your bachelor's, then you can recall this formula. Okay. The work done for isentropic process. Those who are not familiar with this, so I think you should revise the PK NAG, the basic thermodynamic book, so you can have revision about all the compression formulas and how they have derived.
Can you just write the book name once again? What you said on the screen?
It's PK NAG. PK NAG is a very good reference book for
Yeah, okay.
thermodynamics.
Okay,
PK
okay,
NAG.
yeah.
Engineering thermodynamics.
Yeah.
So what is the, so actually we are doing compression. So value of P2 will be more than P1 and we are using the ideal gas. So the value of gamma is 1.4. For the 1.41 exact value or 1.4 you can consider. What is the value? What is the meaning of this gamma?
Polytropic index.
Yeah. So it is the ratio of Cp upon Cv. Okay. The specific heat constant pressure to constant volume. So the actual process is not reversible, we know. So what is the actual work? So the actual work will be the isentropic work upon efficiency. For the isentropic compressor efficiency lies between 75 to 80%. Okay. So this will be the actual work isentropic upon efficiency of isentropic compression. For the real gas, if you are having real gas, then we need to introduce the factor Z1. So it will be introduced. And also the value of K will change because we are considering the real gas behavior. So the value of K depend on temperature and pressure. So the value of K will also change. So we have considered K1. Then if the pressure changes from P1 to P2. So this K1 is at P1 pressure. For P2 it will be different. So we have taken the K1 average value. Okay, the average will be K1 at T1 P1, then at T2 P2 by 2. So this value we have taken for the real gas isentropic work calculation. So if you are having isothermal compression, then the formula is RT ln V2 upon V1. For van der Waals gas equation, then RT ln V2 minus B upon V1 minus B plus alpha upon V2 minus alpha upon V1. These are the constant. So those you can calculate from the this model, van der Waals gas model. For the isothermal, RT upon P1 P2 Z upon P dP. So similarly, the value of average Z average value. So there is a graph that is showing the work of compression with respect to the pressure. Okay. So you can see this one is for the ideal gas. The green one is for the Z factor. And considering the isothermal, okay, this one is for the van der Waals considering the isothermal, and this blue one is considering the isothermal for ideal gas. So we can see for the ideal gas, for the isentropic, the work seems parabola is like having a very high initial slope and then high value. So it's maximum work. For isothermal, you can see it's minimum. So our actual process will lie in between them. And what do you think? Any other information you can see from this graph? Anybody? Please tell me. So this one information we have seen here, that the for the ideal gas and for the, like, if this isentropic and isothermal, how is changing. So what is the second information that we are getting from this graph? So this graph is showing data for the work
So,
of compression versus pressure. Yeah.
so nothing specific for a real gas scenario then.
Okay. Real gas, like we have considered the Z factor. So it depend on the factor. So also we have considered the van der Waals gas equation. So this, they are considering the real gas, but the value of Z is not fixed here. So, but the my point is, what what is the next, like the second information, that suppose if you are just only visualizing this, just don't like forget about the real gas, ideal gas, everything. Just only use the mathematical calculation. You are having a graph, you are having x-axis and y-axis. So what kind of information you can understand from this graph? That's important.
Slope is different for different conditions.
Yes, nice.
For
Yeah, Deepak, do you want to say something?
yes, actually, I not
Uh,
gone through the thermodynamics, Mr. PK Nag, but I understood in at the time of the school in 11th class the thermodynamics means sorry work done is in isothermal condition is a minus RT log n V2 by V1 that time, but in this I'm showing is a plus RT log n V2 by V1. I'm not able to understand why that time is mentioned is a minus.
So maybe because it's the value of logarithm, maybe you have read v1 upon v2 there.
Still, I remember the my V2 because the V1 volume is changing from V1 to V2.
Yeah,
So
volume is
that
changing from v1 to v2.
right.
So if you change this ratio,
Hmm.
so if you take ln v1 upon v2, then what will happen? A minus sign will come outside.
Okay, then I can put in this case is like a P1 divided by P2 in place of V2 by V1, right?
So it will be like minus rt ln v1 upon v2.
Okay, and
Yeah.
I also replace V2 by V1 by P1 by P2, right?
Yeah, because if you are considering the ideal gas and isothermal condition, then you know P1 V1
Hmm.
upon T1
Equal to
equals to
P2.
P2 V2 upon T2. So T1 T2 will be cancelled out.
Correct.
So yeah, so then you can find the relation for V2 V1.
Okay, okay. So
Yeah.
work done can maybe in isothermal may be negative, right? It might be volume is decreasing.
Actually the work will be, because if you are doing the compression, then the value will come in negative only. So if you calculate, because V2 is decreasing, the V1 is
Mm,
more. So the
correct.
logarithmic value will
Negative,
be less than
negative.
zero. So it will come negative. So automatically there will be negative sign will be there.
Correct,
Uh,
correct, correct.
Sir, actually, the work done by the system is the positive, and work done to the system is negative.
Correct. That is understood in 11, 12,
Yeah.
right? But I gone through, I compare the both equation in 11th class and now there is a difference of minus. That what I confuse.
Yeah. Okay. I will check, but
Hmm.
only thing is that it depend on the value actually. If you put the value in this, so the minus automatically come. If you put the V1 upon V2, so V1 is more, V2 is less, so it will be greater than uh, 1. Okay, value will be 1, so the value will be positive, so that why you need to place the minus. Okay, because if you change the in log, if you change the ratio, then we can put a minus sign outside.
Definitely, definitely, I understood. But I'm saying in case volume is decreasing, for example,
Mhm.
V2 is less, V1 is higher. Definitely will I get the minus here. Okay.
Yes,
But
yes, yes.
in sometime we actually volume is increasing. The volume in increasing, it means I
So that is
applying the
expansion. That is expansion, not
expansion.
compression. Yeah, that
Correct,
will be the
correct,
expansion, not compression.
correct, correct. Okay.
Okay. Okay. So let's come to the point again. So the basic information that you can get from this graph, I think two or three of you have already pointed out regarding the slope and all. And so if you compare that the pressure is increasing, okay, and this y-axis showing the work of compression. So if you compare like from 0 to this point, like suppose 300, see the value of work of compression is very high. If you compare with the 300 to 600, so see the change. So from 0 to 300, you need to put this much of compression, this much of work, but from 300 to 600, only this much of work. From 600 to suppose from 400 to like 800, this much of work only. So this thing is very important. So it is showing that if your gas is already at a higher pressure, then to go for a much higher pressure, you need to apply less compression as compared to when you start the compression from 0. So it's very important. So when we were dealing with the underground hydrogen storage, so there we have come through the we have come on the point of cushion gas, and we have discussed about that. So this is the purpose. So if we apply a cushion gas, we can store hydrogen at a higher pressure. Then suppose if we want to deliver it at some higher pressure, then the work done that will be there, that will be lower actually. Okay, because suppose if I can storing the hydrogen at 600 bar, and I need to deliver it at 800 bar, so I need to only deliver this much of work. Okay, as compared to see from the 0. So this is the difference. This parabola is also representing this data. So it's better to store your hydrogen at a higher pressure. So now the
It's
workflow.
basically non-linear compression, compressible fluids and non-linear compression. That's what we get from this graph.
Yeah, yeah.
Non-linear, but
It's
directly proportional to increasing the pressure, right?
yeah, it's
Uh,
parabolic. Yeah, but it's yeah.
yeah.
So the actual work of compression lies between the theoretical limits. So there are theoretical limits, isentropic, isothermal. So the actual work will lie between this. Okay, because we know that when we compress, the temperature will always increase. Okay, so any compression cannot be fully isothermal. There will be some heat transfer to the surrounding also. So heat exchange with surrounding will be there. So it cannot be fully adiabatic. And also we know that it's not reversible. There will be friction, viscous losses will be there. So it's not isentropic. Okay. So the actual work will lie between these limits. So if we are considering the hydrogen compression and we want to, because we know that we cannot have a fully isothermal process compression, but we know that the work will be minimum for isothermal compression. So if the temperature remain constant, so what we can do, we can do the compression in stages. Okay, so in between we will apply the intercooling and try to reduce the temperature. Okay, so we will try to have more stages. Each stages will having a intercooling and try to reduce the temperature each time, so that we will have a kind of, you can say, isothermal system in the compression, so that the work will be reduced as compared to the direct compression. So there is a polytropic index n that is used for this. So the polytropic work will be n upon n minus 1 RT1 P2 upon P1 n minus 1 upon n minus 1. So in this n is the polytropic index, the actual work will be higher. So there is a polytropic efficiency. So gamma upon gamma minus 1 multiplied by the polytropic efficiency. This is the relation. So final T increase on compression, cooling required to reduce work of compression. So if we are having suppose 3 P1 to P3, so we are going through P2 also. So P1 to P2, then P2 to P3. So basically two stages. So first stage, second stage. So for the optimum value of this intermediate pressure, it should be P2 equal to root of P3 P1. So then it will have the optimum value. So it is multi-stage compression with intercooling if perfect temperature same after each stage. So here after each stage the temperature is similar. So basically we are trying to have the isothermal condition. Now compute the isentropic compression work considering hydrogen as an ideal gas compressed from 10 bar to 80 bar at temperature 298 Kelvin, value of R 8.314 and gamma equals to 1.4. Anybody, are you solving? Is anybody trying to solve? Let me show you the formula again for isentropic work. So yeah, this is the formula. Gamma upon gamma minus 1 RT1 P2 upon P1 to the power gamma minus 1 upon gamma minus 1.
So coming around 7013. 13.
7013.
Since yes. So maybe we can consider 7036 because some
Yeah, right.
value after decimal.
So let's see. So the correct answer is A. Yeah, your answer is correct. So here we have given the value of gamma. value of R we have given, T we have given. Okay, so as P2 upon P1 is in numerator and denominator, so unit will be cancelled. So both pressure are in bar, so don't need to, so there is no need to convert into like Pascal or any else unit. Directly you can put this value because bar and bar will cancel out. So put the values 1.4 minus 1 upon 1.4, value of R 8.314, temperature in Kelvin 298, then P2 upon P1, so 80 upon 10 to the power 1.4 minus 1 upon 1.4 minus 1. If you solve this, then you will get approximate 7036 joule per mole. So the correct answer is A. Now identify the correct equation for isothermal compression work using calorific equation of state. So there is also a calorific equation of state. So for isothermal compression, the work is given by the H2 minus H1 minus T H2 minus S1. So we directly take enthalpy in case of this directly using calorific equation of state. Okay, so the correct answer is B. Which of the process is considered for gas expansion process in turbine? Which of the process is considered as for gas expansion process in turbine? Isenthalpic, polytropic, isentropic, isothermal.
Isothermal, sir.
Polytropic.
Isentropic. Uh, Actually, it is a isenthalpic. Actually, enthalpies remain constant. The temperature is only reducing.
If enthalpy remain constant, then how will this turbine will produce work?
Yes, correct.
So we consider the isentropic actually. Okay. So we consider isentropic, but in actual it is not isentropic. So there is an isentropic efficiency. So from that efficiency, we can calculate the actual produced work. Okay.
So actually, the gas when it expands, it actually heats up in case of hydrogen. So is my
So
understanding correct here?
so it depend on the Joule Thomson coefficient, the value of Joule Thomson
Right.
coefficient. So
Right.
so there is a inversion temperature like this. So if your temperature and pressure like coming in this range, then it will be heating, and if
Right.
it is in this range, then it will be cooling. Okay,
Right. Right.
so this depend on the Joule Thomson coefficient. So for hydrogen, I think we have already covered what was the value for hydrogen. Let me go back to the initial slide. Yeah, so the for hydrogen, the value is 202 Kelvin, and it is negative at room temperature. So it will heat up.
It will heat up, right, sir?
Yeah, when you do the expansion. So actually it's very interesting phenomena, Joule Thomson coefficient effect. So those who are want to learn more about it, you should read about it.
Thanks, sir.
Okay. So we consider isenthalpic expansion in throttle wall. Okay. And isentropic expansion in turbine. The salt caverns are developed by which method? Solution mining, horizontal drilling, fracture rock structure, heap leaching.
Solution mining.
Yes. The correct answer is solution mining. Cushion gas is injected into an underground hydrogen storage facility at which time interval of hydrogen injection? Along with hydrogen injection, after hydrogen injection, before hydrogen injection, any time.
Before hydrogen injection.
So what is the purpose of cushion gas?
Uh, it provide during returning back when coming back the hydrogen, it provide the pressure to come out the hydrogen.
Yeah, so we have covered like there are so many benefits of using cushion
Yeah.
gas. So this is one of that benefit. So we should have we have to pump it before the hydrogen injection. Then only it fulfill its purpose. Otherwise, it's of no use. Which of the following is not used for underground hydrogen storage? Salt caverns, depleted oil and gas reservoirs, aquifers and tube trailers.
Tube trailers.
So we have covered already the salt caverns, depleted oil and gas reservoir we have covered, aquifers we have covered. So tube trailers are not used for underground hydrogen storage. So tube trailers can be used for road transportation. Which among the following fields is pure underground hydrogen storage facilities based upon salt cavern storage method? Clemens, Benz, Dedimant, Ketzin. So you need to, we have covered this slide, but it's direct. You need to remember the names. It's A, Clemens. The Joule-Thomson coefficient is expressed by which of the following expression?
C, sir, C.
Yeah. So it's rate of change of temperature with pressure at constant enthalpy. So option C. Select the correct relation between temperature and pressure of two states in isentropic process for real gas. What is the relation for isentropic? So T2 upon T1 equals to P2 upon P1 to the power gamma minus 1 upon gamma. So if we are using the real gases, then we need to introduce the compressibility factor. So the value will be Z2 upon Z1 multiplied by P2 upon P1 gamma minus 1 upon gamma. So for isentropic, as entropy remain constant, so for ideal gas, you can consider relations like P Vk constant, P Vk P1 minus k equals to constant, Vt k minus 1 equals to constant. But for real gas, P Vk1 constant, then Vk2 minus P ratio 1 minus k2 constant, and Vt k3 minus k1 constant. So for the isentropic exponent, this T2 upon T1 is this value, where k depends upon the type of gas, temperature and pressure. The required work of compression is minimum in which of the following thermodynamic process: polytropic, isentropic, isothermal, adiabatic.
Isothermal.
So we have covered this already, that the compression work is minimum for isothermal and it is maximum for the isentropic. The answer is isothermal. The intermediate pressure in multi-stage compression with an intercooler is given by
It's a P2 is equal to square root of P3 P1.
P2 equals to P3 P1 to the power 0.5, or P2 equals to square root of P3 P1. The correct answer is A. Okay. The expansion of gas using the throttle valve or Joule-Thomson valve is your voice is not clear. Please repeat. Isenthalpic. So the expansion of gas using throttle valve or Joule-Thomson valve is, we know that it's isenthalpic process. The value of Joule-Thomson coefficient for the ideal gas is
0.
Yeah, the value is 0. Multi-stage compression with intercooling in between stages can result in decrease in required work of compression, increased temperature doesn't affect work of compression, increase work of compression.
Doesn't affect the work of
Yes, sir.
compression.
Okay, we have one answer. Does it? Uh, sorry.
Decreases.
Decreases. So I think one of you is saying decreases, and one of you is saying doesn't affect. So if the
Increases.
okay, so now everyone agree with the decreases. So it's right, yeah. So it decrease the required work of compression, because we know that the minimum work of compression is for isothermal process, but we cannot have a fully isothermal process, but we can try to achieve that by applying intermediate stages and doing intercooling. So actual process can be approximated by isothermal or isentropic process. Work of compression minimum for isothermal process and maximum for isentropic, and multi-stage compression with intercooling saves the work of compression. So this is for today's class. So if you have any doubt regarding your previous week assignment, you can email me. I will try to reply as soon as possible. Okay, and please don't share me any question that is due for submission. Okay, only
Yeah.
the assignment question those have already completed or submitted, those you can ask.
Can you show me problem number 1 to 4, please? 1 to 4 only.
Yeah, this one.
Yeah, yeah. Oh,
So in this we discussed about the
mhm.
density of liquid hydrogen.
Okay.
So liquid hydrogen density is 70.9. Okay,
Okay.
but
This is based on data, not calculation. Okay. Next, problem
yeah,
number 2.
so it's the operating pressure range for storing hydrogen salt cavern. So it is based on the lithostatic pressure.
Okay. Third.
So number third is what are depleted oil and gas reservoirs. So as we know that it's depleted oil, so it means it will be hydrocarbon. So it will be either option B or C. So but we know that for any underground storage,
Mhm.
the kept rock should be impermeable. It should not be permeable. So option D will be wrong. Option B is right.
Okay. Second answer is right, right? Okay.
Yeah. And this is the
And
fourth. For isenthalpic expansion of real gas with attractive molecular attraction, the Joule-Thomson coefficient is positive.
E. Okay.
So I think we have 10 participants in our class today. So anyone, do you want to share something? Have you used this learning from this course in your industry or in your workplace? Is this course beneficial to you?
Yes, sir. So we have
Okay.
Very much.
recently commissioned.
Yeah,
So we
Chandrasekhar
have
or
recently commissioned.
Yaswant? Yeah, Yaswant, please. Yeah, Yaswant.
Sir, am I audible?
Yeah, Yaswant, you are audible, please.
Yeah, we have recently commissioned a hydrogen refilling station for fuel cell electric vehicles, which produces hydrogen by cracking methane and
Okay,
then
where?
purifying the. This is in this is for IOCL Faridabad R&D Center,
Okay,
and
okay,
yeah, there we are compressing it up to 550 bar pressure.
550 bar.
Yeah, because
Okay,
that's
so
a
it's for just pilot projects, or I think in market, do we have hydrogen vehicles right now?
it's for the pilot, sir, because
Pilot scale
there are long distance trials which are currently happening
currently happening. Right, right.
for hydrogen fuel buses.
Yeah,
So this
right, right.
caters to that requirement of fuel
Yeah.
cell electric vehicles.
So so you have you are using there the methane cracking, right? Methane
Yeah, so
decomposition.
basically there is a sort of compact steam methane reformation unit, which we get a natural gas or we get CBG actually from Indian Oil. So
Okay,
this comes in cascades. So that is basically used as a feedstock, and then we crack that, separate out the CO2, purify the hydrogen, and then compress it to 550 bar for storage purpose. And
nice,
then it is
nice.
dispensed at 350 bar into the vehicles which are under test.
And which technology you are using for the purification? PSA?
PSA, sir, PSA.
Okay. So are you
Yeah.
familiar with the PSA? What is the pressure? Because we have, I think we have studied it is for more than 20 bar for the
Yes,
hydrogen
yes.
purification.
Yeah. So the PSA is much at a lower pressure. That is somewhere around 10 to 12 bar pressure that the PSA unit is deployed.
And have you calculated the efficiency of your PSA? The
No,
separation
we are just,
efficiency?
yeah, at the moment we are just establishing the performances. So
Okay.
we will thereafter be going into the
Because suppose if
specific.
you are using the lower pressure, then maybe your purification is fine. But your separation, but you will having so much losses, I think, at lower bar. But
Yeah,
it depend on the filling. What kind of filling you are
true,
having
true.
in your PSA?
So the details I'll have, but the challenge that typically exists when you crack methane, especially from the sources which are bio in origin, the impurities are a bit unpredictable. So we need to
Right.
have a system which is much more reliable, because certain components like CO2 and all are sort of not permitted for the fuel cells and
Yeah, you
moisture
need to
and all.
remove moisture CO2
Yeah.
completely. Yeah.
So
Yeah.
that is
Because
a higher
if you are
priority.
having the CBG, if you are having the
Correct.
CBG, so for CBG, the government mandate is that the methane will be more than 90% and up to 4% CO2 can be there.
Correct.
Yeah.
So that, and often what happens is this, there is not very stringent control on the CBG source. So that brings about a bit of a practical challenges,
No,
because
but
of which we.
if you are having the CBG, then the supplier itself giving you the CBG. So
Yes.
he already having some kind of process, purification process. So I think you will have only CBG that will only have the methane and CO2 mostly. No sulfur will come into that actually, because the
No,
sulfur
actually
will be less than
we
20
also get
ppm.
yeah, no, we also get sulfur, because that's what the source is, still not as, sort of that reliable for CBG,
No,
and
I
that
think
gets.
if you are getting more than 20 ppm of sulfur in your
Yeah,
CBG, then as per the government norms, you cannot call it CBG. So
true,
I
true,
think
true.
you have to complain because
And
the supplier of that CBG is not following the norms.
correct, correct. No,
Yeah,
we had certain corrosion issues and all those things, which establishes that the sulfur content is much more than the
yeah, yeah.
norms. But yes, those
So,
are being addressed. So I'm not saying that that is
mhm.
something which is but these are the sort of initial teething issues in establishing
And
such system.
what about, are you also having like some sort of, because you are doing the methane cracking, then you will have solid carbon?
No, at the moment, there is no, this being a sort of a pilot, there is
Pilot
no
scheme.
intended use for the carbon, but maybe they, at a
Okay.
later date at the R&D center, they may have some sort of a
Yeah,
application
because
or, yeah,
it can be used for like carbon credits for and all. You can also use that carbon for, I think now we are having various kind of process in which this
right.
carbon can be used. Yeah.
This is a very compact station. Actually, it delivers about half a ton of hydrogen in 24 hours. So, and this is for refueling station applications kind of thing, wherein you can produce hydrogen
Mm-hmm.
on site
On
using
site.
either natural gas or biogas,
Mm-hmm.
bio-CNG.
Right, right.
Sir, my
Nice. And
request,
yeah.
uh, my email ID, which I had furnished earlier, can that be changed? How do I go about this? Because I
So
have missed out many.
in this NPTEL.
Yes, sir.
Okay, so if you want to change any email ID in this NPTEL, then you need to email them. So I think you are having a contact ID for NPTEL, the NPTEL support team ID,
Okay.
email ID.
Uh,
So just email them. They will look into this.
Fine, sir. Could you help me with this email ID, sir? I mean, that would, or else, how do
So
I?
maybe next time I can give you, but
Yeah,
you can just search now. You are having
I'll
your
do that.
course, this course, and in
Yeah,
that contact, I think you can find there.
sure. I'll do that, sir. Yeah. And sir, the previous assignments and this, I think certain things are locked. I was traveling quite extensively, so I couldn't do address those in time. So can it be unlocked, or maybe?
No, no, no. There is due date, because if you are
Ah,
planning to give an exam for this particular course and you want to have a certificate, then you need to follow the instructions. So each assignment is having a due date. You need to submit before the due date. Then only it will be counted for the evaluation.
I see. I see. Yeah.
Yeah.
Fine, sir. I'll drop a mail to the.
Okay. So you are working in which company?
So this is JNK India.
JNK India.
Yeah.
Okay. Okay. Anybody else? So I think we are about to
Oh,
finish. If
oh,
anybody else want to say something.
yes. If I just want to know, P1 is a initial pressure and P2 is a all final pressure. And I need to understand like that
Yeah,
whether
P1 is the
P2 is
initial pressure. Yeah, P1 suppose before compression, P2 will be the after compression.
Okay, in all the cases, we not consider whether section or compression, right?
Yeah, if we have given like compression, then P1 is the initial, P2 is the final.
Okay.
Okay, then thank.
Amit,
Yeah,
sorry,
yeah.
I have probably an out of syllabus question. Where can I find the list of electrolyzer manufacturers in India? This may be an out of syllabus question.
So list of
So,
electrolyzer manufacturers. So you can do one thing. So I don't have the direct list, but you can go to the
sir, I
MNRE
can,
website.
Sorry?
Yeah,
yeah, we deal with electrolyzers, whether it's PEM or the pressurized alkaline type. So I can help the gentleman in case he needs
yeah.
Yeah.
So
something.
you
Sorry,
can
can you give
contact
me
with
can you
Yaswant.
just tell me your mobile number?
So please don't
Yeah,
share your mobile number over this team because this team is being recorded. So
Oh,
it will
correct.
be
Okay.
on YouTube. So it's better if you contact because personally, because in these teams, I think you can message also personally message.
you
It's
can
possible. I think yeah,
you can connect me over LinkedIn or something. It's H1 Natekar.
yeah.
And JNK Renewables.
Yashwant Nadekar. Okay. Yeah.
Natekar, NATEK. Yeah.
Okay.
Okay. So if you want to like for because now we are having a national green hydrogen mission. So I'm sure that you will find some information on the NGHM web portal. So try to find some information on that portal, MNRE portal.
NGHM.
Yeah, MNRE NGHM, National Green Hydrogen Mission. So they are
Okay.
having a separate portal for this. So in that portal, I think they have mentioned the current projects, current manufacturers, those who are putting tenders and all. So you can find details there.
Okay.
Yeah,
MNR.
MNRE, Ministry of New and Renewable
MNR.
Energy.
Okay.
MNRE.
Okay.
Yeah, yeah.
Okay.
Okay. Thank you, everyone. Thank you for joining this class and
Thank you, sir.
yeah, thank you. So next,
Good day to you. Thank you.
so we will meet next Sunday. Okay, from
Yeah.
4 to
Yes. Yes.
6.
Yes. Yeah. Good. Thank you.
Okay.
Thank you,
Okay.
sir.
Bye bye. Thank you.